British Rail are developing trains that fly. No wheels. They lift off the rails to a constant gap, 15 millimeters, by powerful electromagnets, which we can illustrate by reference to this little ball, which is an ordinary beach ball to which there's been attached a metal cap capable of attraction by this electromagnet, which I will shortly switch on, and then the ball can be held up against the magnet. So if I switch the mains on, the electromagnet is now activated, and if I put the ball within the range of the magnet will pull the ball up, and it will actually stay fixed against the magnet. If I try and pull the ball away, it's quite difficult, but with a good pull it'll come. And if it's too far away, it will fall. If it's too near, it will simply bump up against the face of the magnet. So it's rather unstable in any intermediate position. And what British Rail would like to do would be to have a suspension which held the ball or the train at a fixed gap. Now that can be achieved if you have a light system here going from this light to a photoelectric cell, which actually controls the current in the electromagnet in such a way that if the ball goes towards the magnet, the current is made less and the ball falls away slightly. And conversely on the other side. Now if I can start it off in the right position, it will in fact hold that gap, which I hope you can see, quite closely, and I can turn the ball without any interference, and that's the principle of magnetic levitation. Now, it's not enough just to get the train off the rails, of course. The train has to move. So how about that? Well, for that, the proposal, and indeed the result, is to use an induction motor, a linear induction motor. But first, let's look at an ordinary rotational induction motor, which is shown here. It consists of a casing. A number of electromagnets are spaced around the casing, and alternating current is fed into the magnets in such a way that a magnetic field is swept around the casing, rather like a brush with bristles pointing inwards, rotating at a speed determined by the frequency of the current. Now, that magnetic field intersects elements in the rotor and induces currents according to the experiment that you've just seen. Those two currents interact with certain forces. The forces can't move the stator, but they do in fact drive the rotor round in pursuit of the electromagnetic field. And that's the principle of an induction motor. However, the train has to move in a straight line. So the next stage is to say, well, we'll make this into a linear machine. Imagine that this casing is the stator with the electromagnets spaced around it, and if I cut through the casing and lay it flat, then I have the basis of a linear induction motor. The poles are now spaced along the length rather than around the circumference, and by feeding alternating current in the correct phase along the length, then I get a traveling magnetic field which drives the rotor or some small object picking up the induced electricity in that direction. And Professor Laithwaite has kindly provided this little demonstration for that. The electromagnets are, in fact, within this little black box. If I switch it on, I produce a traveling field going to the right, and if I put this copper tube in position over it, stop it initially, then it will drive the rotor round and round as the forces affect the lower part of the tube and put it into quite a fast rotation. However, that's not quite the answer yet. So to get the train to move, then if we put that plate on the top, I'll switch the machine off to begin with, so everything is nice and stationary. And if I now switch the machine on, the traveling field will now drive the plate off in that direction. You're quite safe. It doesn't go that far. At least it hasn't so far gone that far. And it fires away. So that if we had a very long track with electromagnets spaced out appropriately, then we could in fact drive the train with that propulsion.